A patch of sky smaller than a fingertip can contain more worlds than all the stars the naked eye has ever seen. A place that seems completely black is actually like the locked door of a library burning with light. When Hubble stared at a dark region for many days, roughly 3,000 galaxies suddenly appeared. Later, deeper observations revealed nearly 10,000 galaxies within an extremely tiny slice of sky. Some extrapolations suggest the observable universe may contain as many as around 2 trillion galaxies. By ordinary intuition, a sky this dark should be almost completely empty. Yet each faint speck may be a city of stars containing gas, dust, and countless planetary systems. If a telescope opened its eye for only a few seconds, most of those faint galaxies would disappear. If ancient light never reached the instrument, the farthest pages of cosmic history would remain sealed forever. And as space keeps expanding, many distant regions will find it increasingly difficult to send any signal here. Yet photons that began their journey billions of years ago are still quietly falling onto telescope mirrors. Telescopes patiently collect each particle of light, like librarians rescuing pages that have almost faded away. The longer the exposure continues, the more darkness unfolds into an ocean of structures the human eye never knew existed. This is the realm of galaxies, islands of light scattered throughout the observable universe. They are confronting distance, time, and cosmic expansion in a struggle carried out through light itself. For most of history, humans knew the sky only through a few thousand stars visible to the naked eye. The Milky Way appeared as a silver mist, but no one knew it was the combined light of countless stars. The first telescopes broke through that mist, transforming a vague glow into a densely packed field of stars. Then other cloudy patches appeared, too faint to distinguish as gas, stars, or distant systems. Some imagined them as island universes, but their distances could not yet be measured reliably. A great question slowly formed. Were all nebulae inside the Milky Way, or was the Milky Way only one galaxy? To answer it, astronomers needed standard lights whose true brightness could be inferred. Variable stars in Andromeda showed that the spiral cloud lay far beyond the dimensions of the Milky Way. The Milky Way immediately lost its unique status and became one member of a population larger than anyone had imagined. A galaxy is a system of stars, gas, dust, and invisible matter held together mainly by gravity. Inside each system, stars move for thousands of years without ever knowing an observer exists. Some galaxies contain only a few thousand stars, while giant systems may hold trillions. They take spiral, elliptical, or chaotic forms, each preserving a different history of gravity. Young galaxies are often small, irregular, and intensely bright because star formation is highly active. After the early universe, gravity began pulling slightly denser regions of matter together. Dark matter created invisible gravitational wells where ordinary gas fell inward and gradually accumulated. As the gas cooled and compressed, the first clouds became dense enough to form generations of stars. New starlight slowly cleared neutral gas, turning the dark universe into an increasingly transparent space. Small systems collided, merged, and grew, leaving behind stellar tails and violently disturbed gas. From those collisions, the cosmic library began to be written in stars, dust, and long-lasting orbits. The human eye collects light only for an instant, so objects that are too faint remain below the threshold of vision. The first response was simple: build larger mirrors to capture more photons in the same amount of time. Photographic plates continued accumulating light long after the observer stopped looking through the eyepiece. Long exposure turned time into a bucket, patiently catching droplets of light from immense distances. The silence of night became an advantage because faint signals emerged only when stray light was reduced. Tracking mechanisms had to rotate with precision, keeping the target still while Earth continuously turned beneath the telescope. But the atmosphere ripples like water, blurring light from distant galaxies before it reaches the instrument. That is why observatories were moved to high mountains where the air is thin, dry, and far from artificial light. The collected light was also split into spectra, allowing astronomers to read the source's composition and motion. Spectral lines shifted toward red, showed that the space between the galaxy and the observer had expanded. Redshift became an indirect ruler, helping arrange galaxies by distance and cosmic era. Instead of studying isolated objects, surveys began photographing wide regions of sky systematically. Astronomers counted galaxies in small samples, then compared different fields to detect possible bias. If one region represented the sky as a whole, its observed density could be extrapolated across the entire celestial sphere. However, the faintest dwarf galaxies were easily missed, making direct counts consistently lower than reality. A galaxy invisible in ordinary light may still appear in infrared, radio, or X-ray observations. Radio telescopes listen to cold gas and energetic sources that human eyes can never perceive. Infrared telescopes see through dust and capture ancient light stretched to longer wavelengths by expansion. Placing telescopes above the atmosphere removed most turbulence and opened the way to more stable, deep images. Hubble became a sufficiently steady eye to stare for long periods into dark regions few had previously chosen. Deep observation does not begin with luck, but with selecting a field containing few nearby stars and little dust. A bright foreground star can overwhelm distant galaxies that are millions of times fainter. The observing field must also avoid the Milky Way's plane, where nearby stars and dust hide the universe behind them. Once the target is chosen, the telescope must hold its direction through many orbits and hundreds of exposures. In a famous experiment, Hubble spent many days staring into a patch of sky that appeared to contain nothing. Each individual frame was still filled with noise, cosmic rays, and defective points unrelated to the real sky. The frames were compared so one-time streaks could be removed, while recurring signals were preserved. Even a tiny misalignment between exposures could turn a faint galaxy into an unrecognizable blur. When hundreds of exposures were stacked precisely, real signals strengthened while random noise gradually weakened. The result was no longer empty space, but a wall of light covered with distant galaxies. In the same frame, mature nearby galaxies appeared beside young systems from the universe's early ages. Deep observation is like looking through a narrow tube. It reaches very far but samples only a tiny fraction. So the experiment was repeated in other directions to test whether the first field was truly representative. Later programs expanded the area, increased exposure time, and combined more wavelength bands. The longer the observation, the more the telescope reaches galaxies that are smaller, redder, and earlier. The Hubble Ultra Deep Field eventually revealed nearly 10,000 galaxies in an apparently ordinary patch of sky. Each filter preserves part of the light, helping distinguish young stars, warm dust, and older populations. Color in astronomical images is a controlled translation of data, not always the color the human eye would see. Images only suggest a distant galaxy. Spectroscopy is needed to test exactly how much its light has been stretched. Computers identify shape, brightness, and size, creating catalogs too large to process manually. But algorithms must be tested with artificial galaxies to measure how many faint objects they fail to detect. From the missing fraction, models estimate the galaxy population lying below the telescope's detection limit. That is why the total number of galaxies is not a finished count, but a conditional range of estimates. Conservative assessments suggest at least hundreds of billions, while deeper models can raise the total into the trillions. The shelves beyond sight are not seen directly. They are inferred from the pages still bright enough to read. The basic mechanism is simple. Light needs time to cross distance before reaching an observer. Because that speed is finite, every image in the sky carries information from an earlier moment. Sunlight arrives after several minutes, while light from Andromeda has traveled for more than 2 million years. A galaxy billions of light years away appears as it did before Earth and the Sun had formed. A telescope does not see what that galaxy is like today, only the version it sent into space long ago. So deep observation does not merely cross space. It drills directly into the layered past of the universe. Throughout a photon's journey, the space between galaxies continues expanding. Expansion stretches the wavelength of light, shifting it from blue toward red and eventually into infrared. It is like a spring of light being stretched along with the expanding fabric of space beneath it. This is not simply a galaxy flying through emptiness. The scale of distance between systems is itself changing. A larger redshift usually corresponds to light that traveled farther and left its source in an earlier era. The first galaxies emitted visible light, but expansion shifted much of that signal into the infrared. Webb is kept extremely cold, so heat from the telescope itself does not hide the weakest infrared signals. Its enormous shield separates sunlight from the mirror, creating one hot side and one cold side. The segmented mirror gathers faint light and focuses it into cameras sensitive to wavelengths invisible to human eyes. The spectrograph separates the light of individual galaxies, even when many sources appear only as tiny red points. Within those spectra, elements leave absorption or emission features like physical fingerprints. The shifted positions of those features reveal how much the light was stretched during its journey. A red point in an image is only a candidate. Spectroscopic confirmation turns it into reliable evidence. Sometimes nature provides an extra magnifying glass. The gravity of a foreground galaxy cluster bends the light behind it. The cluster's mass curves space-time, forcing background light rays to follow different curved paths. This effect can make a background galaxy brighter and larger, revealing an object that would otherwise be too faint. The curved streaks in deep images are not strangely shaped galaxies, but light distorted by gravity. A single distant galaxy may even appear multiple times when its light follows several curved paths. To recover the true brightness, astronomers must model the mass distribution of the entire lensing cluster. In the young universe, the first galaxies formed from small gas regions inside dark matter structures. Young stars produced intense radiation, heating and ionizing the gas surrounding their galaxies. Many early systems were only compact, luminous clumps, very different from the orderly spiral disks seen today. Gravity pulled small systems together, making collisions and mergers central engines of galactic growth. Gas carrying angular momentum can flatten into a disk where spiral arms feed regions of star formation. Major collisions can destroy disks, randomize stellar orbits, and create smooth elliptical galaxies. Color and spectra reveal whether a galaxy is actively forming stars, aging, or emerging from a recent burst. Dust absorbs starlight and re-emits it at longer wavelengths, making a bright galaxy appear dark. Infrared observations recover the energy hidden by dust and improve estimates of star formation. Most of the mass stabilizing a galaxy's rotation does not shine, so dark matter appears only through gravity. Rotation speeds and gravitational lensing allow astronomers to measure the unseen mass surrounding a galaxy. On the largest scales, galaxies are not spread evenly but concentrated along long filaments of the cosmic web. The web's intersections become galaxy clusters, while the spaces between them open into immense cosmic voids. A deep image is therefore both a slice of space and a sequence of eras layered together. In that library, near and distant books do not tell the same chapter even when they share one frame. Every observational achievement is constrained by one non-negotiable fact: light travels at a finite speed. The observable universe includes only places whose signals have had enough time to reach us since the early cosmos. Although light has traveled for roughly 13 billion years, the visible region is much larger because space expanded. The observational horizon is not a material wall, but the boundary of information that has had time to arrive. Beyond that horizon, countless galaxies may exist, but none of their photons has ever reached a human instrument. An observer in another galaxy would have a different observable bubble, overlapping with Earth's but not identical. For a very distant galaxy, its present state may have changed completely without Earth being able to know. A field that is too small may pass through a dense cluster or a void, distorting the measured galaxy density. Nearby stars, faint galaxies, and detector noise can sometimes look alike, making classification fragile. The most distant galaxies often span only a few pixels, so their true shapes are almost impossible to see directly. Heat, electronics, and cosmic rays can all produce false signals at the weakest detection threshold. A finished deep image is the product of many calibration steps, not a single untouched camera exposure. Colors are assigned through filters to communicate data, so the viewer is looking at a scientific translation. Every galaxy estimate depends on assumptions about the brightness, size, and evolution of unseen populations. Dwarf galaxies dominate in number but emit little light, making them the hardest population to inventory. When two galaxies are merging, the boundary between one system and two depends partly on definition. A bright young clump may be an independent galaxy or merely a star-forming knot inside a larger system. Galaxies are not permanent objects. They lose gas, shed stars, merge, and sometimes stop forming new stars. Because mergers continue, the number of galaxies in the same volume can fall even while total mass increases. So asking how many galaxies exist must also include two questions: at what time and under what definition? Expansion is accelerating, causing unbound cosmic structures to separate at an ever-increasing rate. Light emitted today from some extremely distant regions may never overcome the expanding space between us. The cosmic event horizon marks a deeper limit where future communication becomes impossible in principle. In the far future, many galaxies beyond the local group will gradually fade from the view of later observers. Every cosmic inventory is therefore a temporary snapshot of a universe that is changing and only partly visible. The confrontation with these limits became clear when Hubble was instructed to stare at an almost empty patch of sky. Telescope time was limited, so devoting many days to that darkness was a risky decision. If the region truly contained nothing, hundreds of valuable orbits would produce only a black image. The chosen field avoided bright stars, Milky Way dust, and familiar sources that could overwhelm the deep background. Hubble locked onto the field and continued observing as Earth rotated and day changed into night below. Each orbit provided only a limited window before Earth blocked the target and the telescope had to resume later. Faint photons accumulated on the detector, carrying images that had left their galaxies billions of years earlier. The first frames still resembled visual snow, crossed by bright streaks from high-energy particles. After alignment and cleaning, recurring points remained fixed while false noise vanished from the field. Then the darkness opened, not into a few stars, but into a dense population of galaxies. The Hubble Deep Field ultimately revealed roughly 3,000 galaxies in an extremely small region of sky. That patch was so small, it could be covered by a tiny object held at arm's length. Some systems showed clear spiral arms, while others were distorted as gravity tore and mixed them together. The most distant galaxies looked small and chaotic, recording an era when large structures were still being assembled. Each distance layer represented a different age, turning a static image into a record of billions of years of evolution. The empty patch was chosen because it seemed unremarkable, yet it became one of astronomy's richest archives. If similar densities appeared in many directions, the full sky had to contain far more galaxies than direct counting could capture. Later, deeper observations raised the number of galaxies in the same kind of slice to nearly 10,000. Data accumulated over many years were combined, pushing the depth limit farther without building a new telescope. Wider surveys reversed the strategy, stitching many small fields into mosaics containing hundreds of thousands of galaxies. Yet even those images still missed most of the small, faint galaxies predicted to exist in the early universe. After correcting for what was missed, some models raised the observable total into the trillions. The shocking part is not only the number, but that almost no direction remains truly empty when observed deeply enough. The Hubble Deep Field changed the meaning of darkness. It became a limit of sensitivity rather than an absence of matter. But every galaxy that appears reminds us that another unread layer still lies below the threshold of brightness. After that discovery, deep observation became a standard strategy rather than a gamble made with leftover telescope time. Hubble was upgraded with more sensitive cameras, extending its reach into red and near-infrared light. Large ground telescopes took targets from deep images and spent hours measuring the spectra of individual faint sources. Adaptive mirrors changed shape continuously to correct the atmosphere and sharpen tiny objects from the ground. A single region of sky was studied across many wavelengths because each kind of light reveals a different part of a galaxy. X-rays expose hot gas, stellar explosions, and matter falling around actively feeding black holes. Infrared light reveals dust-hidden star-forming regions and ancient signals shifted beyond visible wavelengths. Radio telescopes measure cold gas and dust, showing how much material remains for future star formation. When the data are combined, a faint galaxy becomes a system with an age, mass, dust content, and star formation history. Massive galaxy clusters are used as natural magnifying glasses to hunt systems below ordinary sensitivity limits. These deep lensing fields expand the search, but they also require increasingly accurate gravitational models. Webb was designed to continue exactly where Hubble is weakest: infrared light from the earliest cosmic eras. Operating far from Earth allows Webb to remain stable, cold, and continuously aimed into deep space. Cold instruments reduce thermal background, allowing extremely faint infrared photons to stand out more clearly. Webb quickly found many bright galaxies in eras where only a few faint candidates had previously been known. Some confirmed sources existed when the universe had experienced only a few 100 million years of development. Imaging finds candidates, while spectroscopy confirms their era through strongly shifted light features. Some early galaxies were brighter and more developed than expected, forcing models to reconsider initial star formation rates. Surprise does not automatically break cosmology. It shows where data and models need closer testing. Modern science does not protect old numbers. It lets new evidence continuously revise the picture. The first misconception is that every point of light is a star. In deep images, most faint points are galaxies. Each galactic point contains countless stars, so a tiny image can hold thousands of separate stellar cities. The figure of 2 trillion is not a photograph containing every galaxy, but the result of statistical extrapolation. Changing assumptions about dwarf galaxies, brightness, or mergers can significantly alter the total estimate. The observable universe is not the whole universe. It is only the part that has sent information to us. The edge of the map is not where space ends. It is where current evidence stops. Looking farther does not mean seeing a more distant present. It means observing an older moment. A red galaxy is not necessarily naturally red. Its light may have been stretched by expanding space. Astronomical images are not imaginary artwork, but neither are they untouched colors from an ordinary camera. Dark matter is not a dark cloud blocking stars. It is invisible and known through its gravitational effects. Galaxies are not evenly isolated. They form groups, clusters, filaments, and enormous voids. Human smallness before this scale does not mean meaninglessness. Recognizing limits is itself a form of strength. The modern turning point is realizing that stronger telescopes are not enough. Science must look deep, wide, and across many wavelengths. Deep observations find the faintest objects, while wide surveys reveal whether they are common or confined to special regions. New survey generations aim to map billions of galaxies, not merely to count them one by one. Automated systems filter oceans of data, but training samples and detection biases still require human scrutiny. Multi-object spectrographs can measure many galaxies at once, turning flat images into three-dimensional distance maps. Instead of asking only how many galaxies exist, astronomers track how they appear, grow, and fade over time. Comparing many eras shows that the count is only one slice of a longer story about the transformation of matter. Simulations are used to expose observational bias, not to replace evidence with a universe invented by computers. The better question is shifting from an absolute total toward distribution, origin, and evolution through time. The observational horizon does more than limit the map. It reminds us that all knowledge is built from finite information. Galaxies may exist whose light will never enter the observational history of Earth. Observers in the distant future may see a poorer sky, even though the universe has not become any less vast. The present era is special, because light from many different cosmic ages is still visible at the same time. Science advances not by pretending to see everything, but by measuring carefully what remains unseen. Under the night dome, one human is only a tiny point before an ocean of galaxies beyond all intuition. Each photon striking a telescope is like an ancient character crossing time to describe a place that has already changed. The cosmic library has never revealed its final shelf. Every deeper look opens another dark corridor. Humanity is small, yet capable of reading a few luminous pages and learning that humility is the beginning of knowledge.